Essential question. We're going to talk about these things called composite functions. The question is, how do you find composite functions? Again, the key three letters is fun. Aren't we having fun? So functions. Now, just a simple definition though of what composite means. You hear the word composite in many different facets of life, not just this class, not just math. So the definition, I think I took it from Google, I just typed it in and here came up the definition, but there's many different definitions, but here's the one that makes the most sense. The combining of distinct parts or elements to form a particular whole. Now I put this word over here, construction, because if you guys have any type of a decking off the back, a porch or anything, they used to make decks out of wood, pure wood, 2x4s and 2x6s and whatnot. Now some of them actually have this thing called composite wood that actually is a composition, a combining of distinct parts. They actually take wood and they take, I think it's plastic, maybe recycled plastic, which is cool, and they kind of combine them to make this really durable material that my older brother built his deck on the back of it, and that's all he used is composite wood, which is pretty cool. Another one that I can speak personally on is sports. I played baseball and played, not now, but I played. Well, they used to have just wood bats, and now many of you guys, if you've ever played baseball, they use aluminum bats. But they come up with this thing called composite bats that is actually a wood/metal, which is really weird. It's not straight up wood, it's not straight up metal, but this is what they've done. They've taken and combined two distinct parts or elements to form a whole. Interesting enough. Another one that kind of came to my mind is not necessarily the word composite, but composers. When you talk about composers in terms of music, you think of like Beethoven and Bach and Mozart, those guys that put these individual distinct pieces of music and they put them together to make this unbelievable cool symphonies, awesome sounding stuff. I'm not a massive classical music guy, but there's some things I listen to that's awesome. So, is an example. And of course, we're going to use it today in math. So, here we go. Let me give you the idea. We're going to look back and remember, this is my function, this is the rule. Remember, the f of x stands for f, well, this right here is f of x. And another way that you can read it is, what is the value of the function when x is something? Remember, I drew this thing over here too. We talked about this thing called a function machine, where we take whatever x it is, the x, and we put that into this function machine. And in this machine, we kind of grind it up, or like a little jack in the box, and it pops up. Well, there's a rule that goes in here that does something with the input. It's kind of like a computer program. And that program happens to be x plus 3. So anytime that you throw into this function machine a value for x, the input, this computer is going to say, okay, I have to do something with it, and it's going to assign a different value and output the f of x value, or the y, same thing, the output value. That's the function machine we talked about. So, if you look at this example, or these examples, here's a couple quick ones. If you find f of 2, what's the value of the function when x is 2? Well, that means you put 2 into the function machine. You put a 2 in for x, that means it's going to output a 5. So I put a 2 in for x. Where there's an x, I put the 2. I put the 2. And then, of course, this is a simple one that equals a 5. Very simple. So f of 3, that means I'm going to put the 3 in for x because it's for this. So 3 goes in for x. And I would get 6. Same idea, I'm going to put the 3 into the function machine, put the 3 in there, it grinds it up, outputs this, outputs a 6. Over here, I know this is weird, but follow the concept. If I find the value of the function when x is a triangle, well, that means I'm going to put a triangle in for x, and I get triangle plus 3. If I want to find f of a house, or whatever, so I put the house in for x. So I have house, plus 3. Nice little door right there. The roof's a little off, whatever. So whatever's here, whatever's here, goes in for x. Check this out. If I want to find f of word, if I want to find f of word, that means I'm going to put word into x. So I get word plus 3. Wow, I just realized this. Did you realize I just wrote the f word on the board? Sorry. F word. Sorry, I didn't mean to swear. Follow the thing, whatever. So F word, you can look at it this way. It's forward. I'm forward thinking. You're a forward thinker. Think of it that way. Come on. So you see that I put word in for x right here, so I get word plus 3. What if I use an expression? And I take x squared plus 1, and I need to put that whole thing into this function machine, so that means I got to put it in for x, no matter where x is. So I'd actually have, if I used a function machine, I'd take this whole thing, and I'd throw it in here, so that means this x is now going to become whatever I'm putting into it. So it's x squared plus 1. Weird. So that means I'd have x squared plus 1. That goes in for x, but I can simplify it because it's not going to output x squared plus 1 because it needs to do what it needs to do, simplify it as much as possible. So it'd actually take the 3 and the 1, add them together, and it would say, oh, there's all I can do. Boop. It's going to output it, so that would be my answer for this. X squared plus 4. Huh. So now I want you to think about this. Anything that is for x, a triangle, the value of the function when x is a house, the value of the function when x is word, the value of the function when x is x squared plus 1. You're taking that and you're plugging it in to the function. That being said, I'm taking two now things, composites. We just talked about that with construction, sports, and music. I take two distinct things and I'm going to make a whole. So now I'm taking this function and a second function and I'm going to make this whole bigger function. Where now I'm looking at, this is f of x, this is g of x, pardon the bell, whatever. We'll get through it. They're changing classes. So I'm going to take this g of x and I'm going to now put that into the f function. What am I talking about? We'll take a look. How you would actually read this is f of g of x. Well, f of g of x. You might also see it sometimes written this way, fog x. That stands for this, f of g of x, just so you know. But now there's two ways to think about that. There's kind of two systems of thoughts in doing these composite functions. I'll show you both. Doesn't matter to me which way you do it. But here's what you can do. Since you know g of x is right here, it's like the triangle, it's like the house, it's like the word that I put in there. That means if I'm putting g of x here, anywhere I see an x in my f of x function, that means I need to put in that for x. So I need to put that in for x. So I really have g of x. I'm putting this g of x in for x. So I have g of x plus 3. Whoa, that is weird. But wait, I know g of x. G of x is this. It's x squared plus 1. X squared plus 1. Oh, look at that. Simple example we just did a little bit ago. So I get x squared plus 1 plus 3. I'd simplify this now and get x squared plus 4. And that is my composite function. I've taken a smaller individual one and another smaller individual one, put them together in a certain way, asking it f of g of x. And I put g of x in for x squared plus 1. Phenomenal. Simplify it up. Now, let me come over here and show you the other way. You can actually look at it and say, wait, if I know f of g of x, and this is my function, x plus 3, f. Cool. So I could take g of x and say, wait, I know g of x is this, so let me put x squared plus 1 in for g of x. And now that means this right here, I'm going to have to substitute in for the x in that function. So I'm just taking x squared plus 1 and saying, wait a minute, I'm putting that into that x for that function, just like we did with all the other ones in the previous slide. So that means I'm going to have x squared plus 1, because I'm taking this whole thing, and now putting it in for x. So that becomes this. And look, it's the same thing. I get x squared plus 4. So they're both the same answer. It doesn't matter to me which way you do it. But there's your two options. So let me do a couple more examples. Composite functions. Example 2 and example 3. Okay, I've changed the functions. H of x is now 2x plus 6. M of x is now x minus 7. There's a question here. It says, does order matter? Meaning, if I do h of m of x, get it? H of m of x, or m of h of x. So, or Does it matter in which way that they are? Do I get different answers? Well, you'll see. So just as a reiteration, if I have m of x, that means m of x is the same as x minus 7. So I can take this whole thing and put it in here for m of x. But that now means, okay, my h of x function, I'm going to take this piece right here and put that in for x. I'm just substituting in because I'm asking what's the value of the h function when x is x minus 7. Oh, what did I just say? What's the value of the function h when x is that right there? So that's why I'm putting that in for x. Just like it would say if I'm asking for h of 3. Well, if it's h of 3, that means I'm asking for the value of h, the h function when x is 3. So I put 3 in for x. This, I'm putting the whole thing in for x. That's why it becomes this. Sweet. So as soon as I substitute that in there, notice I put parentheses around it. That's important. I'm only putting this in for the x. So it's 2 times x, so it's 2 times that whole thing. So then I just must distribute. Distribute, pardon the bell, whatever, we'll get through it. So I get 2x, and I get minus 14. Phenomenal. And then, of course, I just simplify my combine my like terms, and I get that answer right there. So 2x minus 12. Sweet. Now let's see if it's different. Over here, m of h of x. Well, I know h of x is this thing right there. So I'm going to take 2x plus 6 and put that in for h of x and get this. So since this is my x value now, if you will, I'm looking for the value of m, that function, when x, quote unquote x, is that goofy thing. So I got to take that and substitute it in there. Boop! There it is. So that's this is actually pretty simple. So now I can take 2x plus 6 minus 7, just combine my like terms, and I get negative 1. So notice, I get 2x minus 1, and I get 2x minus 12. They are not the same answer. So what that tells you is that the order in which you do them matters. Okay? I'm not talking permutation or combination. I'm talking about in terms of composite functions. So there you go. Let me give you another example. A little bit more to help make some more sense of this. So I've changed the functions. Actually, I'm going back to the original one. A little bit more intense question. So the f of x function, if you remember, was x plus 3. The g of x function was x squared plus 1. Now, I'm asking you to find the composite function of g of f of x. You also might see it written this way at some point. G O F X. Golf. Golf of x. So, here's what you do. I know f of x is x plus 3, so I'm going to take the x plus 3 and put it in for, oh, there it is. Sweet. Since that right there is in my g function, so now I'm going to take this, and I have to put it and substitute in for the x into this particular function right there. So now this is an interesting one, because notice what I'm doing. You have to put parentheses around this that you're substituting in for x, because x is being squared. So now I'm putting this whole thing in for x, bam, right there. So I have the quantity of x plus 3 squared plus 1. Well, let's do x plus 3 squared. And I did that right over here. So remember, the square means I multiply the base by itself twice. Bam, bam. Full one out. And you get x squared plus 6x plus 9. So that whole thing right there is what this goofy thing is. So I have x squared plus 6x plus 9. And then I still have this plus 1. Sweet. So let me just simplify it out. X squared. Simplify everything I can. Combine my like terms. And there, ladies and gentlemen, beep, is my answer. Sweet. So there you go. That one's a pretty cool one. Just make sure you remember, use parentheses and put it around it. Okay? Let me slide this aside. And the last one, I want you to pause this video now. After I explain these examples, I want you to do them, and I'll give you another video to explain the answers. But here's your two functions. I've changed them. F of x now is 3x to the 1/3. G of x is now 8x to the 2/3. Ew. Again, yuck. So 2/3 is that exponent, 1/3 is that exponent. The questions are these, 3 of them. I want you to find the composite function, f of g of x, rock and roll, and then, oh look, I'm switching on you, take and multiply the two functions, ooh, and then divide the two functions, ooh, and see what you get. Good luck. I believe you can do it. Rock and roll.